Hello everyone, good morning. Welcome to the GATE Metallurgy problem set 15. And this is the first problem. For the ideal gas, the plot that is non-linear is. So these are the four options, and in each case we have to draw the plot and we have to check whether it is linear or non-linear. Okay. So the first plot is PV versus T. So we know that PV equal to nRT, and if we draw PV versus T, then it will be equal to Y and it will be equal to X, and this is constant nr, that is Y equal to mx. So this is the graph of Y equal to mx, and we know that Y equal to mx, this will be the straight line passing through the origin. So this will be the PV and this will be the T. So in first case the graph is linear, but we have to find which of this graph will be non-linear. So A will not be our correct answer. Okay. Now coming to B. PV versus P at constant temperature. Again PV equal to nRT, and we have to write PV versus T at constant temperature. If the temperature is constant here, then nR is already constant and T is also constant, so the whole expression is constant. So PV will be equal to constant. If the temperature is constant, PV will be equal to constant. So if we draw PV versus P, okay, at constant temperature, then the value of PV is always constant. It will not depend on the value of pressure. So this will be equal to like that. It will be parallel to the x-axis because the value of PV is constant. But remember, this is only at constant temperature. So definitely this is also not a non-linear graph. Coming to the next, that is the option C here. P versus V at constant temperature. Now we know that PV equal to nRT, and if the temperature is constant, okay, so this will be equal to P equal to, let this is constant, so this is K, let K that is constant, V. So if you substitute P as a Y and V as a X, then it will be equal to P equal to Y equal to M by X. That is Y as K by X or M by X. That is the M is the slope or the constant. So in that case, we know that Y equal to 1 by X or the K by X. This graph is rectangular hyperbola, and you might have learned in the graph. So this is the P versus V at constant temperature. This will be rectangular hyperbola. This will not cut this axis also. This will be asymptote, and this will be non-linear. So the correct option is C. Also let's check the fourth one, that is lnP versus lnV at constant temperature. If the temperature is constant, so this is the case, then Y, that is the P equal to constant K YV. If we take the log, that is the lnP will be equal to lnK minus lnV, and this, if this is Y, so this is C and this is X into M. Okay, so slope will be -1 definitely, because this is -1 into lnV. And in this case, since the slope is negative in this case, okay, since the slope is negative and this is the intercept, so this, let this is the lnk, that is the intercept from here to there, slope is negative, so this will be like that. So again this is a linear graph, so the correct option is C here. Coming to the next problem, and the problem is, in thermite process iron oxide is reduced to molten iron by aluminum powder because, so basically this is the thermite reaction and it is used to join the railway track. Okay, that is Fe2O3 plus aluminum, that is in powder form, it will give Al2O3 plus Fe. Okay, the Fe is produced in molten state. Okay, that is used to fill the gap, and when it gets solidified a weld joint is made. Okay, so iron is reduced to molten iron because here the oxidation state of iron is +3 and here the oxidation state of iron is 0. So the oxidation state changes from +3 to 0, so this is going to be reduced. Okay, and for the aluminum this is 0 and here it is +3, so aluminum get oxidized. So this is a type of redox reaction in which iron oxide get reduced and aluminum get oxidized. So one is reduced and other is oxidized. So why the reduction of iron is so easy? Okay, in this case the reason is the melting point of iron is low. No, definitely not. The melting point of iron is high, that is around 150 degrees centigrade. The reaction is highly endothermic. No, this reaction is highly exothermic. This is not endothermic because a lot of heat is produced. This is very vigorous reaction, that is explosive reaction, and that reaction should not be done in a closed room. It should be done outside the room, you can say in open atmosphere, open environment. Large amount of heat is liberated in the formation of Al2O3. This is absolutely correct because this is highly exothermic. Delta H is negative, that is very highly negative, and this is a spontaneous reaction, so we know that delta G equal to delta H minus T del S, and for the delta G to be less than 0. Okay, for the highly spontaneous reaction this should be less than 0, and this, the value of this should be highly negative, and this is also very highly negative, so this reaction is highly spontaneous. Okay, that is explosive. So the large amount of heat is liberated in the formation of Al2O3. This is absolutely correct because this is highly exothermic. So a large number of heat will be liberated in this case. Aluminum is an amphoteric element. Absolutely correct. Amphoteric element is that element which react with acid as well as base. So for example, when you react aluminum with HCl, then it will form LCl3 plus H2 gas. This is also correct. If you react with aluminum with sodium hydroxide, then sodium metaaluminate NaLO2 will be formed with the evolution of hydrogen gas. So both the reaction takes place with the aluminum. So aluminum acts as an acid as well as base. So this is an amphoteric element. Like zinc also, zinc is also amphoteric element. So this is also correct, but this has nothing to do with this redox reaction. Okay, because this is not an acid base reaction, this is redox reaction, and for the feasibility of this reaction should be highly exothermic. Okay, and absolutely this is highly exothermic, and the main reason behind it is very great affinity of oxygen with aluminum. In the previous lecture of the Lingam diagram, we have learned that in a Lingam diagram the aluminum lie at the bottom. Okay, because the affinity or the oxide of aluminum is very stable. That's why it's lie at the bottom. So it has great tendency to react with oxygen. So aluminum just extract the oxygen from the Fe2O3 and itself gets oxidized. For example, Mg also, it has very high affinity for oxygen. Okay, and if you take dry ice, that is the solid CO2, and if you burn Mg in dry ice while keeping it on dry ice, on the slab of dry ice, okay, so this is the slab of dry ice and this is the Mg, suppose, and if you heat it by using the gas burner in a closed container, then Mg will continue to burn even in the absence of oxygen, because Mg has very great affinity towards the oxygen and it will just take out oxygen from the CO2 and will form NGO, and the CO2 by losing oxygen will get converted to carbon solid. So when you just remove the slab, you will get the small chunks of small parts or the particles of carbon on that dry ice. Okay, so that's the end of this lecture. Thank you very much.